If you work in RF, you are literally surrounded by it every single day, whether you realize it or not. It's so common, it's almost easy to take for granted. So today, we're going to pull back the curtain on one of the most fundamental concepts in our field, vertical polarization.
Now, where are we getting all this from? Well, this is actually part 10 of a 20-part series, and it's all based on a really detailed report on radio frequency propagation by the folks at RFI Detectives who are part of Virtualization Options, LLC. This stuff was developed for technicians and engineers like you, so we're definitely drawing from some serious field expertise here.
All right, so let's start with something you've probably seen 1,000 times, but maybe never really thought about. The whip antenna on your car, the antenna on a boat, that handheld radio you use, they're all sticking straight up. They're all vertical. Why is that? That's not a coincidence. It's a very deliberate engineering choice.
To really get why that choice is so critical, we've got to be absolutely clear on what we're talking about. So let's just lock in the fundamental definition of what vertical polarization even is. And you know what? It's a beautifully simple concept when you break it down. When we talk about vertical polarization, all we're really talking about is the orientation of that electric field, the E field. As you can see, it's just oscillating vertically, straight up and down, perpendicular to the ground. And it's this simple orientation that leads to both its biggest strengths and its most significant weaknesses.
Okay, so we get what it is, but the big question is why? Why is this specific orientation the absolute go-to choice for pretty much all mobile communications? Let's dive into the practical advantages that make it so dominant out in the field.
And this right here lays out the reasons perfectly. First, the antennas are just simple. Whips, monopoles, they're easy, they're inexpensive to make. But the real magic, the real game changer, is that omnidirectional pattern. A vertical antenna radiates equally in all directions on that flat horizontal plane. So for a car or a person with a handheld radio, you don't have to aim it. The signal just works, no matter which way you're facing. That makes it absolutely perfect for anything that moves.
And let's be crystal clear about this. It isn't just a preference. The RFI Detectives report states it as plainly as you can. It is the standard for land mobile and maritime communications. So if you're designing for these environments, vertical polarization isn't just an option. It's your fundamental starting point.
But, as any engineer will tell you, there is no free lunch in RF. For all of its advantages, vertical polarization comes with a very specific set of limitations that can cause major problems if you don't understand and manage them.
And here is the crucial trade-off. That same vertical orientation that makes it so great for mobile means the signal interacts directly and powerfully with the ground. Suddenly, the Earth's surface isn't just something you're transmitting over anymore. It becomes an active and often pretty disruptive part of your signal path.
Yeah, this slide breaks it down really well. First, when that wave bounces off the ground, you can get a phase reversal. And what does that mean? It means the reflected signal can actually cancel out your direct signal, creating dead spots. Then, in complex places like cities, every reflection from a building can twist and degrade the polarization. This creates what the report calls polarization scrambling. Just a messy, unpredictable signal that is an absolute nightmare to work with.
So, what does all this lead to? Well, it leads to something that the source material identifies as one of the most common and most damaging mistakes made in the field: polarization mismatch. It is the silent killer of system performance.
I mean, just let that number sink in for a second. 20 to 40 decibels of loss. We are not talking about a little bit of static or a small drop in quality. This is catastrophic failure. This is the difference between a perfect connection and no service. It's what happens when a receiving antenna is installed horizontally for a signal that was transmitted vertically. And listen, no amount of amplification can fix this fundamental mistake.
Okay, so that's the theory, right? The good, the bad, the ugly. But how do we turn this into a practical tool? What's the takeaway for you, the engineer in the field who's deploying and troubleshooting these systems every single day?
It really boils down to this simple 3-step mental checklist. First, know your application. Is it mobile? It's going to be vertical. Second, analyze the environment. A flat rural area is a completely different RF world than a dense urban canyon. And finally, and this is the most important one, physically verify your polarization match. It sounds so basic, I know, but as we just saw, overlooking this one step is one of the costliest mistakes you can possibly make.
So I'll just leave you with this final thought to chew on. Think about your own networks. That one site that always has performance issues, or that link that never quite seems to meet its budget.
Could a simple, silent polarization mismatch be the root cause, just hiding in plain sight? It's definitely worth checking.